Hello and welcome everyone to this year's last BRAG general meeting. Those of you who recently become our member, BRAG stands for Berkeley Research Administration Group, and its mission is to provide a forum for collegial interaction in the research administration community. We do this by facilitating presentations by subject matter experts, creating an environment to foster peer-to-peer exchanges, and by seeking and sharing best practices. Our today's guest speaker is Mechanical Engineering faculty, Professor Francesco Borrelli, and he will share with us his research work on predictive control for automated driving, robotics, and food and energy system. So before I hand it over to Sarah to introduce Professor Borrelli, let me go over a few housekeeping rules. There will be time for Q&A at the end of the presentation. So please add your questions to the chat box and as they come up, and we will get to them at the end. However, if you want your questions to be anonymous, so please feel free to send us a private message to Sarah and me directly, okay? And with that, I will request Sarah to take it over from here.
Thanks, Sanchita. So quick introduction. Francesco Borrelli received the Laurea degree in computer science engineering in 1998 from the University of Naples, Federico II in Italy. In 2002, he received a PhD from the Automatic Control Laboratory at ETH Zurich in Switzerland. As Sanchita said, he's currently a professor in the Department of Mechanical Engineering here at UC Berkeley. He's also the author of more than 200 publications in the field of predictive control and the author of the book Predictive Control, published by Cambridge University Press. He is the winner of a 2009 NSF Career Award and the winner of a 2012 IEEE Control System Technology Award. In 2016, he was elected an IEEE Fellow, and in 2017, he was awarded the Industrial Achievement Award by the International Federation of Automatic Control Council. Since 2004, he has served as a consultant for major international corporations. He was the founder and CTO of Brightbox Technologies, Inc., a company focused on cloud computing optimization for autonomous systems. He was the co-director of the Hyundai Center of Excellence in Integrated Vehicle Safety Systems and Control here at UC Berkeley. And he's the founder of WideSense, Inc., a company focused on e-mobility. And again, as Sanchita said, his research interests are in the area of model predictive control and its application to automated driving and energy systems, which is what we'll be hearing about today. So thank you for joining us, Francesco, and I will turn it over to you.
Thank you, Sarah. Thank you, Sanchita, for inviting me. Good morning, everybody. Thank you for the nice introduction. A pleasure to you about my research today. I have put together a set of slides at a high level, and we can keep this very interactive. I'm known for self-driving cars, and so if you have any questions on self-driving cars, Cruise, Waymo, some of the company sponsors my labs. For some companies, I do consulting, so I'll be happy to answer any of your questions. Let me start sharing my slides. I have too many windows open. Where are my slides? Here they are. Can you see my screen?
Yep.
Okay. One second. Okay, I was telling my son not to yell too much. Okay, here's so this presentation is about predictive control systems, and I am going to start with a definition of a control system. Okay, here is what I used to teach in my basic class at UC Berkeley. It's called a block diagram, and a controller is an algorithm, some software that sends inputs to a plant based on some information sensed from the plant to achieve a desired behavior. Okay, it's a general concept, and the plant can be really anything. Could be a car, could be your house. And this is what I study. I study control. This block here, I study control system. I study the software that helps controlling any plant. Okay, let's make a few examples. We'll keep this simple here. This is your Nest thermostat. I don't know how many have a Nest thermostat. In this case, the plant that you're trying to control is the temperature of your room. It's your room, okay? It's your home, it's your office. And we know that at Berkeley, this controller doesn't work really well sometimes for your office. But if you have a Nest controller, so this is the software that is in this device that will decide when to turn on and off the heating or the cooling system based on a temperature that you measure from your room. Okay, so the controller here design is the software that goes in your Nest thermostat. So it actually turns out that this object is a controller as well as a sensor, because there is a temperature sensor in a Nest thermostat. Let's do another example. This is your rice cooker. And this was one of the Japanese ones, Roshi, that they write AI and artificial intelligence or fuzzy control. There's a smart logic controller here inside this device that makes sure that your rice is cooked at perfection. And so the controller here controls how much heating to provide to inside the system here. So how much to heat your rice. The plant here is this device here. And what we sense, there is a humidity sensor inside. I don't know if you ever tried to open before to see if it's cooked. You see this vapor going out. So there's a humidity sensor, and based on this information, the controller makes sure to stop and provide the right heating to your system so that your rice is cooked to perfection. That's your controller, is the software that controls this device. This is a zoom of a cruise control on your vehicle. Every car in the world, every modern car has a cruise control. Not many people use it. You see, there's a button, and you are at a given speed. You push the button, and the car will keep that speed, whether you're going downhill or uphill. So especially truck drivers use this cruise control a lot. So the control is the logic that controls the plant. The plant is the vehicle in this case. So the input in this case is acceleration and pedal. Even if you don't see the accelerator and the pedal moving, this is a digital signal that goes and changes the speed of your engine of the vehicle. And so what you sense is from the wheel sensor, you sense what is the speed of your car. So the controller tries to keep a constant speed based, if you push this button, based on your latest speed. So these are three control systems. And what's interesting about control theory, this is why I was always fascinated, is that you don't have a control theory for heating, ventilation, or a control theory for rice cooking, or a control theory for cars. There is just a control theory. We teach how to design these controllers regardless of the plant. Do you have questions? Do you have any? So this is the field where I work on. It's actually a pretty broad field. It's in electrical engineering, computer science, as well as in civil engineering. I was hired by a mechanical engineering department, but I'm actually have a bachelor in electrical engineering and computer science. There are the former Dean Shankar Sastry was a control system person. There are at least 12 or 15 control faculty at Berkeley, and there's a lot of controllers. Then, because this is really the core, the brain, people think of control being a big part of AI or artificial intelligence. Do you have questions? I'll stop here for a second. I want to keep this interactive. I will try to be. I have a lot of slides, but I'll stop at 45. Okay. So what is a predictive control? This is like now go to the future. Is a control. These are the controllers before are pretty simple. You can buy them, and you can buy this device. There's a logic, and they usually would not hire a graduate student. I cannot write a proposal on a rice cooking control system. But I studied predictive control system, which is a control system that models uses models to forecast what's happening in the future, and the forecast change the behavior of the system. So let's make again an example. If you are driving, this is our first experiment that worked on a self-driving car. If you are driving, you see I'm not touching the steering, and then I'm not touching the pedals here. And if you're driving here, you will need, the controls are more complex. Why are they more complex? Because you need to predict what the other actors in the scene are doing. Okay? So is this car slowing down? Is there another car trying to cut in? Should you overtake or not? So the intelligence to control the vehicle needs to be predictive. And so this is the type of technology that I developed in my lab, and we've been studying for over 15 years. Student here is a Tesla, 4 students from Elon Musk this was almost when I started in 2022, hired 4 interns in the summer and from my lab, and they ended up developing what is the Tesla autopilot today, based on these technologies. So I have a book we do when I write proposal. When I write proposal, I usually write proposal about the theory of predictive control, and also how to write the algorithms that run on these devices, and theory to validate these algorithms. So what I want to talk to you about today, I've been doing this for a long time, and our lab has been quite successful in a number of applications. Solar, around 60% of solar power plants around the world run using the algorithms that we have developed. So those are predictive control algorithms. A lot of work in the automotive field, and even also in heating, ventilation, air conditioning, because there is by using forecast information about the weather, you can keep people comfortable and use less energy. So today I'm going to focus about this. It's really on cars, because it's fun, and it's one of my big areas of expertise. But really what the lab does is to use this artificial intelligence, or this predictive control system, for a safer and more sustainable world. So reducing emission, saving lives. It's really what our motto of the lab is. So let's focus on self-driving cars. And you have heard, you probably, if you go to San Francisco, you'll see a lot of them trying to learn to drive around. And I already told you about these experiments. The reason why everybody's pushing for self-driving cars, it's really the number of people that die every year. They're talking about, in the United States, around 40,000 people die, and there are this number actually went down during COVID, and now it's up again. We are actually, probably this year, we're going to hit 50,000 people dead from car accident. Around $3 million people injured. Some of them are really bad. These are bad injuries in the United States and around the world. So imagine, this is roughly, if you put all these numbers around the world, this would be like a Boeing 747 falling from the sky every day. So imagine every day you have the news of an airplane has fell from the sky. So this is really how bad this is. It's just that we are used to this idea that people just die in car accident, and we do not pay a lot of attention. There's another reason why we want to do this, because if human drivers in general are bad drivers because they don't know what is the effect of their emissions on when they use their pedal. So you can actually go slower, you can go smoother, you can be smarter about the route that you take, so that you have less CO2 emission and less energy consumption if you have an electric car. So also there's another reason. When I teach this class, a class of vehicle dynamics of cars, especially the young student, they take Uber, they do not like to drive. And so there is this trend where mobility is now a mix of public transportation, especially in Europe, and shared mobility like Uber or Lyft. So it's an old problem. People have tried and they failed in the past. You see this picture here. this was a this is a picture in 1950. You can see this family. Let me point, take a pointer here. Okay. You can see this family in a trying to play, I think it's backgammon here, and there's nobody driving this car on the highway. So Europe tried in the 80s, 90s. This was a massive amount of money at that time. And again, they failed. And today we are trying again. There's self-driving cars in the news. Some companies have shut down recently, but there's still a lot of interest. It's still one of the most difficult challenge of our times. And everybody's saying it's just a few. It's just some, like people like Elon Musk say, they're not too hard. Some other people say still far away, but there is a belief that at least you can start getting self-driving rides in San Francisco next year from a couple of companies. So let me tell you a little bit about how this works and the technology. How do we help these technologies, and how this technology helps actually other fields like energy and solar plants and agriculture. So where we are today is that if you have a lab like ours, could apply for a vehicle test. This is a DMV. You apply for a autonomous vehicle. It's under $50, but then you need a $15 million insurance. So it's the insurance for a vehicle like this is very expensive. And when I teach, I see that there are chats here. Yes, Cruz is correct. Cruz is doing already. If you are interested, I can see if we can get rides for Cruz, and I'll send you the link how to subscribe on how to get a self-driving ride from Cruz in San Francisco. So when I teach how the driving experience works to my students, I show them this loop and say, because again, some of them have never driven a vehicle. Okay, so I have to tell the human interacts with this object, which is called a car. And the way you interact is, first of all, you interact through a set of devices, which are pedals, okay, accelerator and braking pedals, and the steering wheel. Okay, so by moving steering wheels and pedals, you do something to the vehicle. And today in modern cars, actually these objects, they're like joystick. They're not connected to anything physical. They send signals to your, this will send signals, the accelerator will send signals to your engine. The pedal will send signal to your braking system. The steering will send a signal to the motor that changes the wheels of the car. Okay, so it's all digital interfaces. There's no direct connection. It will be just a signal that will be sent to the motor that says speed up, so that increase the speed of your wheels. So that's what is called an actuation system. But you're not aware of this, okay? You just control these three elements with your limbs. And if you are in Europe, you have an additional element, which is your gear. Now, the low-level control system, what's happening at the low level is some of the things that we study. We are car experts, and so we study, if you push the brake, then what will happen, there is this object that changes the pressure inside. This is called an hydraulic brake circuit. These are super complex systems. And as you change the pressure in here, there is this disc that pushes, and like a clamp, right, clips on these are called the disc brake, and your wheel will start stopping. So we study what is called the low-level control system, the braking system, or the engine system. Now, in one of the cars we have in the lab, you can control the brake at each four-wheel. Imagine a human has only one braking, one pedal, which is a braking pedal. Imagine having four braking pedals. Why do you want to brake each wheel differently? Because this will give you a different behavior of the vehicle, which can be safer. Maybe you want to brake more the rear wheel and less the front wheel. Okay, maybe you want to brake more on one side so you can swerve around an object. So imagine now having access to four braking torques. imagine having trying to decide the engine torque, but now you can decide how much speed, how much torque you want, power you want in the front and the rear. Of course, you control the steering angle, and we control also the suspension. So it's a complex control system. The plant is the vehicle. The software that goes in here is what we design and controls all these elements in real time. Every milliseconds, we change the system by deciding these values. So now that you have controlled the vehicle moves in an environment, and the vehicle is a car, right? So imagine a box moving in this environment, interacts with environments in 3 dimensions. The 1 dimension is with the ground, and these are the tires. We study tire models. They are very complex objects. There are professors that it's called a viscoelastic material. You actually can stretch these tires if you have a lot of force. A vehicle definitely will be able to stretch these tires. So we do simulation of these tires, and we understand what happens to the friction when you go on asphalt or snow and ice. For instance, Cruise and Waymo, which is the company from Google, they're still not able to drive on ice or on snow. It's very hard because you have less friction. So we are going to help them driving on ice and on snow. The other way you interact is to move in an environment in 3 dimensions. And so what you're seeing here, let me stop this for a second. What you're seeing here, this is our car we are driving in Berkeley, and we are collecting data from our sensors. Okay, this data, they are converted. We gather this information. This is converted into, you see these boxes. We are saying, I think this in front of us is a car. Okay, this car that you see here. So then this other object here, these other elements that you measure is a pedestrian. So there's a lot of work on sensing and reconstructing the environment. Your brain does this very well. The control software this is one of the biggest challenges for the control software. To do that, you need a lot of sensors. Okay, let me explain to you what type of sensors you have usually in these cars. You have cameras. Okay, you have a lot of them. The Tesla is up to 12 cameras now. These are the more expensive version of what we use now for Zoom. We have radar. Okay, this uses waves to detect the vehicles around you, and you have laser scanners. This is an old version, okay, that you will put on top of the vehicles and will provide what is called the cloud point. Imagine a laser that every time detects an object, reflects back, and you will measure a point and you will measure the position of that point in a 3-dimensional space. So you also have ultrasound, because there could be little kids hiding behind your cars, and these ultrasounds are very good for this type of object detection. So if you look at if you go to San Francisco and you see a self-driving car from Cruise, you will see all these things on top are laser scanners to reconstruct your environment. And they have cameras around here. They also have cameras here, and they have radar hidden around the vehicle. Okay, so it's a very complex sensing system. The sensing system is used to reconstruct the environment. Okay, now when a human drives, you are closing the loop. You are the control software. You measure your eyes and your sound, your ears will help you understanding the environment. You're saying this is a pedestrian, this is a car, and predicting the environment. Based on this prediction, you're controlling then the vehicles by using the pedal position and the steering. So I've been spending a lot of time trying to understand what happens in our brain, okay, and talking to a lot of neuroscientists. It's very clear to me and to neuroscientists today that we have a model of, even if we learn this model, a model of the vehicle, we basically say, oh, if I turn this thing, the steering of 90 degrees, the car is gonna go left a lot, right? So of a big amount. But if I turn a little bit, my reaction is gonna be smoother. We also have an environment model in our brain. We're really good at this. We predict that if this pedestrian is probably going to cross in the next seconds, or this other group of people is talking, they're not going to cross the road. And so we use a predictive control in our brain. That's why I've always been fascinated by predictive control, because that's how our brain works. So in my first sabbatical, I went around the world and trying to figure out really what neuroscientists knew about the control in the brain, how we were making predictions. And so there's a Charlie Rose beautiful series in 2008 where there's a Nobel Prize on neuroscience that they claim, well, we know that the brain for sure is what is called a neural simulator, is able to predict the future given input, right? So but they had no proof. Okay, at least there is some empirical evidence. Okay, but it's very hard to prove, really, to figure out what happens in our brain. I was just talking. This year was another sabbatical, and I met. This is a work of David Foster, who's a neuroscientist in our department in Berkeley, and I think it's really fascinating work. What he's doing, yes, is putting electrodes in the brain of rats, and then he records the brain activity of the rats. Okay, so here's a rat. What happens then? It does he has this cage. Okay, so the rat will be here, and it will show food to the rat. Okay, but the rat cannot go around. And what he records, it's beautiful. What you see here, it's the neural activity of the brain of the rats before moving. So you can see your predictive control in action. Your neurons, they fire and they predict the plan to reach for food that avoids the obstacles. I think it's very fascinating because this is a very new article. They're talking about this year. And this is the first, I think it's one of the first proof that we make predictions in our brain about our motion. And we have neurons that exactly activate, they represent the spatial location in the future. Again, the rat hasn't moved yet, that's where the rat is, but your brain is predicting forward. A little bit like the Matrix movie. And this was very fascinating because that's what my control algorithms do. They make forecasts and then they act on the system. So so it's very simple. This human does this with a predictive controller. We want to get rid of the human and design a software where you tell him just the destination. This software takes information from the environment and controls the vehicle so that this loop is safer and is greener. Okay, I see there's a chat. Thank you, Sarah. And so again, it's why people are why it's hard and why we are not there yet, because this controller, it's hard to write the software that is able to understand everything, not only to predict what's happening in the environment, but to act on the vehicle so that you're safe. So let me show you, let's see how much time we have. It's 10 minutes. How do we, just to give you a little bit on what is the main idea and how we use that on other systems, including food. I don't think I have many slides on food though. So the idea is simple. I have a model, a mathematical model of the object. I compute an action. I use this model to predict, and then I act on the system. I take some measurement and I keep the process of computing, predicting, acting. Computing, predicting, acting. So the challenge is really how to make this really fast, how the same speed that our brain works. And so here's an idea. There's a soccer game. Let me replay this for you. So this is the brain of a soccer player that is looking, predicting, and acting. Okay, and trying to kick the ball. And you can see how our brain works. Sometimes our we don't do this fast enough because we believe in our forecast, so we actually don't measure what's happening. Let me repeat.
Ja, optische Täuschung, der Ball.
You see, the ball is not there, right? So, but he has executed. Right. So it's fascinating because the brain is executing exactly according to the plans, right? Yes, predicted. I can see these predictions in the brain, but just you didn't close the loop with where the ball was. Right? Okay. So again, this is I love this video because it shows the whole motion plan, right? The motion is planned and executed. It's beautifully executed, just the ball is not there. This is just another proof that we use these predictions and models in our brain all the time. So this is only mathematics I'm going to show today, but it's this when I write proposal, I'll say, well, there is something in it that our controller wants to minimize. I want to, this is my control objective. I want to push the ball very far. Okay, there's a start position, is the end position of the ball, and then there's the motion model, the dynamics, and this is where the hard mathematics comes in. How do you describe the motion of a vehicle? How do I describe that the vehicle needs to avoid obstacles? So this is all the math that goes in here. That's what we study, and for instance, and each problem is different. If you're driving on ice, you want to care about the vehicle dynamics, the low friction. If you're parking, you want to care about a lot about the obstacles around you. If you're driving at very high speed on highway, you want to care about the other vehicles cutting in front of you and which lane you should take. Okay, so that's really the math and when we write proposal that is behind the predictive control system. And let me show you just, for instance, a very simple parking example. We can do this. The parking code, the predictive control, looks like this. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of code. Seems very simple, but there is, in this obstacle avoidance, for instance, element here, there's a lot of math that goes into to understand and to actually write. We came up with this formulation only 5 years ago. Okay, before that was not clear how to solve a parking control problem autonomously. Humans are pretty good at it. Actually, not. This is a video that shows you that sometimes can be really hard. This is the minute. How many minutes it took this person to 6 minutes to get and solve this problem, right? So if you use an automated autonomous parking, and there are some cars that are coming up now with Tesla is already as a summon parking, but this would be very hard also to solve for Tesla. If you use our algorithms, okay, you will see that in exactly the same scene, we reconstructed the scene, the best action using a predictive controller would be this one here, and that's how you get out of the parking in a few seconds instead of 6 minutes. Okay, so and of course we can do this. We've been working with a truck company. Now imagine you want to park a big trailer truck, then use the same algorithms. Okay, this is the powerful of this technology. The only thing that we have changed here is the model of the vehicle. It's no longer a small car, but it's a truck. And so we changed the equation, the mathematics, but the techniques is still the same. I work when I teach these things because it's actually experiments. You'll see some experiments which are dangerous. And we go back and forth with risk. And but we have our little car, so we can do experiments which are safe. And this one cool experiment of a group of students decided, oh, I want to do more complex parking. It's called drift parking. Okay, it's quite cool. This is slow motion. You see that your speed is too high, and what you're going to do, you're going to drift park. Okay, don't try to do that. It's quite dangerous. We actually have big cars doing that. But these are the type of methods they work and we are popular for are methods that actually work at the what is called the limit of handling. Okay. We have, I do a lot of teaching in this area. My next semester, I'm going to teach a class with 170 students where I teach them cars and teach them in this case, the intelligence, the autonomous controller goes into this little box here on top of the cars. We do a lot of outreach activities, undergraduates, high school students during the summer in my lab. They all love writing software that controls these cars. So in the last 5 minutes, I'm going to talk about my proposals are about learning systems. Where does the learning enters here? Because the brain learns, okay? So far, I haven't talked about learning. So learning is this idea in predictive control where you do an experiment and then you adjust your model. This is my son that is trying to learn how to solve a ball in a cup problem, right? It's a kendama. This in Japan they call this kendama. It's a ball in a cup, and it's a quite challenging problem, right? This was Luca. Now Luca is 13, and it's a pain, but it was very nice here. You can see this idea of building in your brain, getting better at it because you make a model, and you know that if you pull faster, then the ball is going to go higher. So there's a lot of research that are doing learning in predictive control, how the models are updated. And you know, these are our robotic experiments that is trying to learn to catch the ball by using a predictive controller. Okay, you do this repeatedly, and as you collect more data, you update the prediction models, and then at the end, you are able to do this very nicely. Okay. So we are popular, been very popular.
So here's an example. I'm not going to play this.
Our lab has been popular with this experiment. Became very popular last year because actually Google DeepMind trying to solve the same problem using artificial intelligence without using predictive control. Okay, and this is Professor Ben Recht at a conference, AI conference, telling how badly the Google DeepMind controller was working, how elegant was our solution. I will stop here. We have a lot of learning experiments. One of the ONR project, Office of Naval Research, we wanted to learn to drive a vehicle at very high speed. And this could be very useful for instance, in rescue missions, okay? And students had a lot of fun. This is a vehicle driving over a circle. First, very slowly. You hear the wheels screeching here. It means you're going at the limit. You can imagine students have lots of fun here. And again, this is a controller is learning to drive faster and faster, which is very important for our Department of Defense. So what am I writing proposals on? Our community believes that the single vehicle, single robot research will happen. And so we always look ahead at what will happen in 20 years. And really the question is about what will happen when these robots will be everywhere. And so what happens when I'm going to have a million self-driving cars, or a million, or you can buy a robot. And so the latest research is really about learning co-robots, collaborative robotics. So this is a robot and a human trying to do a task. Okay, we have a current project. I'm writing more proposals on co-robots. Again, this is a robotic platform on in Echeverry Hall. This is a mobile platform. This is a manipulator, and there is a human and a robot trying to transport this off. It's very complex. The robot has to predict what is your intention. And it also has to sense the environment, and together you have to be safe, right? This could be a very heavy object. The other research is on multi-vehicles. What will happen when many vehicles, self-driving cars will be around, will interact with human-driven vehicles, and you will be able to talk to parking lot infrastructure, be able to have Google calendars of your workplace. And so what will happen in this connected world where vehicles are autonomous? And so just to complete, we have a big experiment with ARPA-E where we're trying to redefine the mobility control system, the intelligence when these vehicles will be automated. And so we have around five cars at Richmond fuel stations. They talk to each other. And we try to control these vehicles so that the driving experience is safer and that you reduce energy consumption. So we actually instrument these cars with fuel sensors. This is a hybrid car, so it uses both fuel and electricity sensor. And we try to measure energy consumption and reduce energy consumption of this vehicle. This is our one, and that will be my last video. This is an experiment that we did 2 years ago. During COVID, we had to stop all our experiments in Arcadia. It's close to Los Angeles. What you see here is 3 vehicles. They're driving autonomously, and they're talking to the traffic light. The traffic light saying, I am red, but I'll become green in 5 seconds. So the 3 vehicles you'll see, they'll start it's called a micro platoon. They'll start smoothly. You see the human driver, okay, probably was distracted with the phone. Instead, the vehicle here are not distracted. They will look at the environment. They'll sense there is a track here, so they'll decide that it's safer when it's safer to change lane based on the tracking for a speed. So this is all. This is a real demonstration. These are on a real city, on real humans, and these 3 cars are 3 cars from the lab that have been controlled by our predictive software. I'll stop here. We're using this technology everywhere, as I mentioned on solar power plants. Here, you want to predict where the sun is and where are the clouds, because because your tracking angles, the optimal tracking angle, which is the one to harvest the most energy of the sun, changes as a function of the light conditions. And so our algorithms are running, as I said, on 60% of the solar power plants around the world. And basically, if you think about it, with predictive control, you can, if you improve 6% of energy efficiency on 20 gigawatt, that's 1.6 gigawatt more energy you can generate because of just better control software. I'll stop here and I'll be happy to take any questions.
Thank you, Francesco. There are a couple of questions in the chat, and I'll just
let me start looking at. That's Tom. You discussed independent braking and for the benefits of 4-wheel steering such as. Yeah, that's amazing, Tom. Thank you for the question. Yes, as a matter of fact, we have models with 4-wheel steering. We are writing a proposal on trying to study exactly this. For the military, they have, one of the challenges that for regular passengers vehicle is still very expensive to have 4-wheel. We are talking about each wheel going independently, right? But that's the future. I think it's a beautiful question. With this one of our in our plans. David is talking about, speaking of LA, it would be more realistic to push towards integrated traffic system. No, but much more widely distributed. That would benefit both automated cars and regular. Very good point. Yes, in better traffic system will be definitely needed. This is actually one of the proposal that we are trying to put together. It's unclear where the intelligence should be. If you start having there are transportation people trying to push with the intelligence, the traffic system level. So what will happen when the traffic system will be smart, okay, then the vehicles can be dumber, right? Because they will take care of you being, they'll assume you're dumb and therefore they will control the flow. Now, what will happen when we have a smart traffic system together with a smart vehicle? That's challenge because the two intelligence can conflict. We already seen this. We learn the traffic system and we adjust our controllers. Now the traffic system learns what we do and they adjust their controllers. So the situation, you can be in an unstable situation. So we don't know today, both government as well as researcher, they don't know the answer. How do you do distributed intelligence in a smart way? Are you smart at the vehicle level? Are you smart at the traffic system level? Are you smart at the city level? Maybe it's the integration of traffic lights and public transportation. Very, very interesting problem. Thank you for the question, David.
And I think there was just one more from Sanchita in the chat, and she says, what are some of the key challenges you've encountered in trying to apply human-like intuition to mathematical models for control system?
Great, yeah, no, that's an excellent question. Our brain has this amazing ability to handle things which work in the continuous world, like a steering, okay? And decision, this will be called logic decision. If I go, you go, then just thinking on this logic, right? Combinatorial, like solving a chess game. And so from a mathematical point of view, the combinatorial words, playing the chess, and what is called the continuous world, a steering, the physics world, is actually one of the most challenging problems we have today. And this is what we struggle every day. Today, a cruise vehicle will still get stuck in a situation with 3 cars. They can reason about, okay, I stop, then you'll go, and then the other car will go, and then I'll go. It's very hard to think in this. We are really good at it, right? Our brain can do this quick thinking of multimodal. They're called multimodal predictions. Vehicles, the most advanced cars out there, they still cannot do it because it's just you don't have enough computing power. And we don't even have actually some of the math behind it still has to be developed.
Interesting. Very good. Thank you for sharing that. Is any other questions? Anybody has any? It looks like, okay. So thank you so much for sharing your amazing research work with us. It was wonderful. And I have to be honest, my son was overhearing that presentation. He just jumped in oh, this is interesting, because he works from home. So he just found, oh, this is very interesting. Can I just listen to your presentation? So there was somebody who was listening who was not part of this group also. So
thank you. It's the joy of doing research. And again, as I said, we have high school.
No, he's actually graduated from college this year.
Okay.
So yeah,
Okay.
so from UC San Diego. But it's almost close to his field. Not really his field, but he found it very interesting. So he joined. He was overhearing and he joined in. So thank you again so much for sharing, and thank you, Sarah, for bringing her, asking her to present. So it was thank you so much. So we are and thank you, BRAC community, BRAC members for attending to this meeting. We really appreciate that could take time to join it. So we will be putting the link to a short survey in the chat, and we will also send it out in an email. So it's Kate or Hannah, will you be putting the link in the chat? Okay, awesome, thank you. So please take a minute to give us a feedback on today's meeting. We will really appreciate it. And also note that our next BRAC general meeting will be in the new year, so likely late January or early February. Announcement will be sent out as soon as we finalize the meeting date and times. So, and if anybody has any questions, if not, then we will conclude our today's meeting. Hope you all have a restful holiday, and we look forward to seeing you in 2023. Bye,
everybody. Thank you. Bye-bye. Bye-bye.